Hello, this is Flight Readiness review for the experiment 26.073b. Thermal insulation efficiency of LHS-1 lunar regolith simulant as a material for lunar habitats in stratospheric near-vacuum conditions. Our team's project for Cubes in Space 2026. In this review, we'll follow our validation plan and then demonstrate live that experiment is fully operational and ready to fly on RB-11.
Our mission supports NASA's Artemis program and its strategy of in-situ resource utilization, building on the Moon using local material instead of launching everything from Earth. Surface temperatures fall to -130 and even -180 degrees Celsius, so any habitat needs strong thermal protection. And carrying all of that shielding from Earth would be far too expensive.
The leading local material for surface habitats is lunar regolith, and it's expected to be an excellent thermal insulator. But its performance has not been tested in near vacuum under flight conditions. Our experiment measures exactly that, how well LHS-1 regolith works as a thermal shield under near vacuum and low temperature conditions that approximate lunar surface.
So our hypothesis is that a sensor shielded by 10 to 16 mm of LHS-1 regolith will cool noticeably slower than an unshielded control sensor, because in near vacuum there is no air between grains to carry heat by convection. To test this, we log 3 channels: under regolith temperature, ambient temperature and atmospheric pressure. For that, each signal needs right resolution. Under regolith sensor reads temperature in degrees Celsius, and the ambient sensor reads temperature in degrees Celsius and pressure in pascals. The payload is a 3D printed PETG cube, the standard Cubes in Space size, about 3.8 cm per side with a total mass of about 50 grams. A plate splits it into a regolith section and a safe section. The under regolith sensor sits behind cube, capsule and regolith, while the ambient sensor behind only cube and capsule. The regolith is the only difference.
The components all matching our application for spaceflight list are the Adafruit QTPy ESP32 SS3 with 8 MB of flash, the BMP388 pressure and temperature sensor in its own capsule, the MCP9808 temperature sensor sealed in its PETG capsule to keep regolith dust out, the Lipley charger BFF, which conditions the external 3.7 volt supply, the STEMMA QT JST cables, brass standoffs and M2 screws, current dust filters in the cable notches and 25 grams of LHS-1 regolith simulant filling the regolith section.
The firmware is the Cubes in Space ION code, adapted for our 3 modules, with no IMU or RTC. We disabled that code and wrote the MCP9808 temperature into an unused field, keeping the data stream length unchanged. Data logs to onboard flash in short bursts between deep sleeps to save power. A multi-hour flight uses only a fraction of the flash. Each wake cycle writes 680 rows of 127 bytes, which is about 84 kilobytes. As one cycle is 60 seconds awake and 600 seconds asleep, it is about 462 kilobytes per hour. Now to the live demonstration. On power up, the firmware initializes both the MCP9808 and the BMP388, takes a baseline pressure reading and starts logging, with no error halt. So both sensors are detected and working. Next, the current draw and power budget. The experiment is powered either over USB-C on the bench or as in flight from a 3.7 volt supply into the charger's JST. RB-11 allows 60 mA on average, and we measured about 41 mA at startup, about 65 mA while collecting, and 4 mA asleep. Because it sleeps far longer than it collects, that averages to roughly 10 mA, comfortably within budget. Then the data itself. Here are the recorded channels: the under regolith temperature from the MCP9808 and the ambient temperature and pressure from the BMP388. Finally, data download. The complete dataset is simply pulled from flash onto the computer. To conclude, the hardware matches our application for spaceflight. It runs nominally, it averages at about 10 mA within budget, it logs all 3 channels, and the data downloads cleanly. In short, the test data matches our objectives, and the experiment 26.073b is fully compliant, operational, and ready for flight.
After the flight, we will write a post-flight report analysis. with 3D models, graphs, and comparative photographs to evaluate how effectively lunar regolith protects from temperature changes. And to share our journey, we will document the build and the flight stages on our social media, creating a blog for everyone interested.
Thank you to the Cubes in Space team, and thank you all for watching.